So welcome you back to today's lecture. So what we were doing so far was we were discussing parametric estimation problems. So if we see parametric estimation problems, you have a set of probability distributions under your consideration. The true probability distribution, that means the data from which probability distribution is coming, or the data is coming from which probability distribution, that is unknown to us. Or in other words, we say that the state of nature is unknown to us. And I am interested in estimating some characteristic of unknown state of nature. So I am interested in estimating theta of f. So where f is the unknown state of nature, what I know is f belongs to a family P of probability distributions. So what I do, based on observations or based on the data, I take certain action, which tells me what would be an estimate of theta of f. So you had a set of probability distributions, you had a set of actions available to us, and each action resulted in certain loss, depending on what the true parametric, true state of nature is. So essentially, if you look at the parametric estimation problem, I had three components. One is a set of probability distributions available to us. Second thing is set of actions available to us. You know, each action corresponds to an estimate of the unknown state of nature or an estimator. And then you had a loss function. So there were three components. You can call this as P, set of all probability distributions, A, an action space, and L, a loss function. Now, in general, any statistical inference problem can be formulated as a general decision problem where I have just three components: set of probability distributions available to us, set of actions available to us, and the loss function available to us. So what I am going to do in next few minutes, I will try to formulate the testing of hypothesis problem as a decision problem. So let us look at how did we study testing of hypothesis problem in your earlier classes. So let the problem is as follows: let x1, x2, xn be a random sample from a PDF or probability mass function f. So to make things simple, for the time being, I assume that f is either f0 or f1. So that means I will be interested in testing simple versus simple hypothesis. So f belongs to P, which is f0. So the question is, to decide whether this sample x1, x2, xn is coming from f0 or f1. To decide whether the sample, so let me write down this as a vector x, which is x1, x2, xn, is coming from f0 or f1. So that means based on the data, I have to take xn that either it is coming from f0 or it is coming from f1. So how many xn's are available to us? There are two xn's available to us. I call them as a0 and a1, where a0 xn says that, look, your sample is coming from f0. Or which is equivalent to saying that true state of nature is f0. So what I am interested in is to decide what is the true state of nature or true probability distribution from where the data is coming. So true probability distribution is f0 or f1. So my action space has two elements, a0 and a1. A0 corresponds to the action that sample is coming from f0, and A1 is the xn that sample is coming from. F1. So there are two xn's available to us, A0 and A1. Now I consider my loss function. Now my loss function would be in terms of L, F, A. So this is a loss function. What are the values f can take? F can take value f0 or f1. And only two xn's are available to us. So A can also take only two values, A0 or A1. So in certain sense, my loss function is a matrix which has 4 elements. So it is a 2 by 2 matrix. So I can write down my loss function as. So here I write down the state of nature, f0 and f1. And here are xn's A0 and A1. Normally I take my loss to be non-negative, and my loss is 0 if I am taking the correct xn. Now it is what should be an element over here? Loss in taking xn A0, that means saying that f0 is the true state of nature, when actually f0 is the true state of nature. So that means my decision is correct, my xn is correct. So in this case, I can take loss to be 0. What is this? I am taking xn A1, that means I am saying f1 is the true state of nature, where actually f0 is the true state of nature. So here I am incurring certain loss because my xn is a wrong xn. My xn is a wrong decision. So I can put it here, some loss b which is bigger than 0. The minimum loss is 0. Now similarly, this is the thing when I am saying my xn is A0, that means I am saying f0 is the true state of nature, when actually f1 is the true state of nature. So I can have another unequal loss, let us say C, over here. And then this again corresponds to the situation when my xn is that f1 is the true state of nature, when actually f1 is the true state of nature. So that means my decision is a correct decision. So in this case, loss could be 0. So I have these three components. Now let's look at what would be a decision rule. Now if you recall what I had said, a decision rule is nothing but a probability distribution on the xn space for every fixed x. So for every x belonging to the sample space, it should be a probability distribution on the xn space. But my xn space is only having 2 elements. So that means it would be a probability distribution of a discrete random variable. So yx is a discrete random variable. Normally yx, because here can take value a0 and a1, you call such quantities not random variable but random element, because yx is not actually taking a real value. So it can take value a0 or a1. So yx corresponds to the xn which I take. Now note that delta of a0 given x, because it is a probability distribution and there are only 2 elements in my xn space A, so delta a0 given x has to be same as delta of a given x. So in certain sense, I can represent my probability distribution delta dot x only by delta x. I can call this to be just delta x, so that I don't have to carry all the time a0 and ax. This is just for simplicity of notation. I call delta a1x to be delta x, so that delta of a0x is nothing but 1 minus delta of. So what it says is, I can describe any decision rule by a function delta from sample space to 0, 1 such that delta represents the probability of taking xn a1. So thus, because here only two xn's are there and you know that delta a0 given x has to be 1 minus delta a1 given x. Since the two are related, I just describe one of them, which is taking xn a1 through delta x, and I call that as a decision rule because then I know that delta a1 given x is same as delta x and delta of a0 given x is same as 1 minus delta x. So thus, a decision rule delta is a map from chi to 0, 1 with the following interpretation. What is the interpretation? That delta x is the probability of taking xn a1 given that you have observed your sample as small x. So that means the sample is observed as small x. So this is also same as probability of taking xn a1 means probability that yx is equal to a1. Right? So 1 minus delta x that way would be probability of taking xn a0 given x equal to x, which is same as probability that yx is equal to a0. So let us consider my risk function. So for risk function, first I have to consider two randomization. One randomization is done by yx or the decision rule delta, and second randomization is based on all possible observed values of the data. So let us first consider the first randomization. So L star theta, theta is my f, decision rule is delta, and observed value of x is this. What is this? I know that this is nothing but expected value of L f yx, because yx, after I have observed x, my xn depends on what is the observed value of yx. Yx is either a0 or a1. So this is with respect to L yx. And what is that? Yx I know takes value a0 with probability 1 minus delta x. So this is same as L f a0 1 minus delta x plus Lf, and my yx takes value a1 with probability delta x, Lf a1 delta x. So that is what L star delta f L star f delta x turns out to be. Let me just use small margin over here. So what I do is, this is same as, I break it into two branches when f is same as f is f0 or f is f1. So I find out L star f delta x for f is equal to f0 and f is equal to f1 separately. So if f is equal to f0, then I have to put L f0 a0 here. L f0 a0 is 0, so this term is not going to contribute. And then L f0 a1. L f0 a1 is same as b times delta x. And when f is same as f1, then in this case, this is same as L f1 a0. L f1 a0 is same as c times 1 minus delta x. So my L star f delta x turns out to be this quantity. So now I find out what is the risk function. So R delta f is nothing but expected value under the probability distribution f of L star delta f, and now I do the randomization over my data x, which is same as b times expected value of f0, because when f is f0, it is same as delta x. If f is same as f0, and it is same as c times let us try to see what is the interpretation of E f0 delta x. Delta x is what? Probability of taking action A1. Probability of taking action A1 means probability of rejecting H0. So delta x is probability of rejecting H0 given x. Then I have taken expectation with respect to x. So this is same as probability under f0 of rejecting H0, which is equivalent to taking action A1. So what does this say? If I look at E f0 delta x is nothing but probability of rejecting H0 when H0 is true, and you call this as a probability of type 1 error. Probability of rejecting H0 when f0 is true, that means H0 is the true value. Probability of rejecting H0. So here what I am interested in testing is H is same as f is same as f0 against f is same as f1. So this is my testing problem, right? So this is a probability of type 1 error. Right? Because you are faced with this problem and you have to take action whether H0 is true or H1 is true. And what is E f0 of 1 minus delta x? Which is probability f0, or let me call this as 1 minus probability of sorry, this would be f1. So I should write down, because I have to calculate here what is E f1 1 minus delta x. E f1 1 minus delta x is nothing but 1 minus E f1 of delta x. And what is this? This is the probability of rejecting H0, that means accepting H1 when actually H1 is true. This you define as a power. So this is same as 1 minus power. So E f0 dx is nothing but type 1 error probability, and E f1 1 minus delta x is power. What do you do in the classical approach or Neyman-Pearson approach? In the classical approach, you fix one kind of, so this classical approach is also called Neyman-Pearson. So best thing would be if I can minimize the risk at both the points. So the best scenario is find delta that minimizes risk at both the points, because risk only has 2 points, R delta f0 and R delta f1. So that minimizes R delta f0 and R delta f1. Both it minimizes simultaneously. But you have seen in your earlier course that it is not possible to find a decision rule which minimizes R delta F0 as well as R delta F1. This is not possible. The way in the estimation problems, it is not possible to find an estimator that minimizes the risk at every parametric point. Here R delta F0 and R delta F1 are risk at parametric point F0 and F1. There are only two parametric points. So here the similar kind of thing happens in the testing problem, that I cannot find a decision rule delta which minimizes risk at both the points F0 as well as F1. Or in other words, I cannot find a decision rule delta which minimizes both kind of errors, R delta F0 and R delta F1. Now note that R delta F1 is nothing but 1 minus power, right? So it is same as the probability of type 2 error. So then what do you do in the classical approach? You try to fix one kind of error and then try to minimize the second kind of error. So a way out is fix one type of error and minimize the second kind of error. So what I do is, without loss of generality, I can assume that type 1 error is more serious. Otherwise, you can interchange the null hypothesis and alternative hypothesis. So I frame my alternative hypothesis and null hypothesis in such a way that type 1 error is more serious. Type 1 error is E F0 delta x, which is probability of rejecting H0 when H0 is true. So what I do is E F0 delta x, I fix this to be less than or equal to alpha, a small quantity. Normally you take alpha to be 0.01, 0.05. So this guarantees that I'm only considering those decision rules for which probability of type 1 error is small. You see, you cannot make probability of type 1 error to be 0. Let us look at a decision rule which makes the probability of type 1 error as 0. So if delta x is always 0, it says whatever data comes, I don't care about the data, I will always, my decision rule is always delta x equal to 0. Delta x equal to 0 means I'll reject all the time H0. If you are rejecting H0 all the time, irrespective of what data you have observed, then probability of rejecting H0 when H0 is true would be 0. But what would be EF1 of 1 minus delta x, which is a probability of type 2 error? That would become 1. So if you try to minimize one kind of error, the other increases. So this certainly cannot be made to be 0. If you want to make it to 0, the probability of other kind of error would just explode. So as a trade-off, you say that, okay, I can bear up to level alpha on probability of type 1 error. And then find delta for which second kind of error, which is EF1 delta x, which is basically 1 minus power EF1 1 minus delta x, is minimum. Or in other words, EF1 delta x is maximum, EF1 delta x is nothing but power is maximum. And that is what exactly you do in the Neyman-Pearson theory. And the solution to this problem is provided by is provided by Neyman-Pearson lemma. And what does that say? Your decision rule delta star x should be how much? It should always reject H naught It should always reject H naught, so that means it will reject H naught with probability 1 if f1x or product I is equal to 1 to, because they are IID, so product I is equal to 1 to n f1xi is greater than k times product I is equal to 1 to n f0xi. You see, one thing has to see, if one has to get this as a minimum or EF1 delta x to be maximum, one should try to exploit the maximum leverage which is available to you. So suddenly, the maximum would be occur among all such tests for a test for which EF0 delta x is alpha, because that is the test which is utilizing the maximum leverage available to it. And then it says I'll reject H naught only with probability gamma. So this is where the second stage randomization is also necessary. First stage randomization, second stage. So it says after you take the observation X, you don't reject H naught immediately. You reject it only with probability gamma if this quantity is same as this quantity. And you don't reject H naught. That means you reject H naught with probability 0 if this is less than. And as I said, this test has to exploit the maximum leverage. So that means where k is such that EF0 delta star x uses the maximum leverage, so this is same as. So this is the classical approach. And why classical approach was necessary? Because you realize that I cannot find a decision rule which minimizes the risk at every parametric point. In testing problem, which was equivalent to saying that I cannot find a test which minimizes both kind of errors simultaneously. So in the classical approach, then what you say is you try to fix one kind of error which you consider to be more serious. Then I said I'll frame my hypothesis in such a way that type 1 error is more serious. You put out a bound on that and then try to minimize the second kind of error, and then you're able to find an estimator which is optimal, subject to this criteria. So what we see is a testing problem can be formulated as a decision problem. Now if the solution which I want is in terms of fixing one type of error and trying to minimize the second type of error, the solution is provided by the Neyman-Pearson lemma. Now what we'll see is what could be the other criteria. If one has to deal with the minimexity, one has to deal with the Bayes rules, and so on, how to deal with this problem. So that we'll do in the follow-up lecture. Thank you very much.